Okay, hi everyone. I was asked one question during the break that I thought I'd repeat the answer for. So remember we talked about these Higgs couplings here, the measurement of this Higgs self-coupling. So as I said, to test that, we need to see H-cubed interactions or quartic H interactions. And this is something that most likely, the quartic interaction is completely out of reach for the LHC or its upgrade. So there's no chance that we'll be able to probe this in LHC experiments. H-cubed right now is at the level of the experimental sensitivity to that is about this. We're sensitive to 5 times the standard model coupling. Okay, so we need another factor of 5 to get to the standard model level. So that's something that is certainly very active, and the LHC, the high luminosity LHC will try probing, but most likely you will need a bigger collider to see that. So that's where things are. So even at the end of the LHC program, there's a very good chance, unless there's something completely new that's happening, that we will not have a full test of the standard model picture of the Higgs sector. Okay. So that's something I wanted to emphasize. And good. And so now we can turn to theory. And we started talking about the Higgs mechanism. And we said that it's actually a very, very simple picture. We have, we add the simplest representation of SU2 cross U1 that you can think of, and it does the job. And now I want to talk about that in a little more detail. So this expansion that I did here, we're actually really separating things into the VIV and the Goldstones, the Goldstone bosons, the G+ and the G0 here, and the physical Higgs. Which I'm denoting by little h. And in terms of how well we've tested each one of these, we already saw that this is actually, the answer is quite different. This part is well tested, and this part we said is sort of not tested or hardly. And now, if we talk about theory, then also from the point of view of theory, this is something that's very well understood. And this is where, because we haven't tested this experimentally, first of all, we don't know whether this is the full picture, but also this is where we have big theory questions. So I want to talk about these now. Okay. So now we're really talking about the theory of electroweak symmetry baking and the questions associated with that. Okay, so we're writing this very simple potential. I think I have the potential somewhere, but yeah, it's over there at the very top. That's the Higgs potential. So that's the simplest, that's the most general renormalizable potential that you can write down for the Higgs, except for what's quite special about this is that you choose the sign of this mu squared term, the MASH term, to be the wrong sign. and you also need to put in a scale by hand. So these are both things that we have no idea about. So this is a potential that we need to put in by hand. We need to put in by hand the potential V of H, and specifically, we need to put in by hand the mass parameter. The mass parameter with the scale mu, which is about 200 GeV, roughly. And notice that this is the only scale that we have in the standard model that we put in by hand. There's no other scale that appears in the standard model Lagrangian. There is a scale, of course, in the standard model, which is lambda QCD. But lambda QCD is generated by the running, or is very naturally generated by the running, if you assume that there is some high scale where you have the alpha QCD as an input, and then lambda QCD appears through a dimensional transmutation as, let's say, some high scale, which can be the Planck scale or the Gatt scale or something like that, times e to the 8 pi squared over the beta function g squared. And if we start from a coupling that's a weak coupling with alpha about 0.1 or so, then this is around 10 to the minus 16, which is precisely what it needs to be. In other words, it's very, very natural and easy to generate large hierarchies of scale from the running, okay? And that's exactly what happens in QCD. So this is a scale that appears in a way that's totally natural, doesn't disturb us at all. We start by writing just this QCD Lagrangian here with a coupling of order 0.1 or so, and we get the QCD scale roughly where it needs to be. So this is the only mass parameter that we're writing in the standard model, which is not very satisfactory. We also need to put in the negative sign, and we have no idea why this is the sign. I mean, we have no dynamical explanation or no understanding of why the Higgs mass parameter in that potential needs to have the wrong sign. It's just an input. And so, if you wish, there's absolutely no difference in writing this Higgs potential as opposed to just imposing the Higgs vid. Okay, it's just a parameterization. The potential parameterizes the fact that we want a Higgs with an expectation value. That's it. And finally, there's the naturalness problem. And what's the naturalness problem? The naturalness problem is the fact that this mass parameter mu squared is not stable or gets quadratic contributions from radiative corrections. So if we calculate mu squared, let me just put, if we calculate radiative corrections to this parameter, we'll get the tree level thing that we put in, and then we get loop corrections from standard model fields, and essentially this has the form of some loop factor times whatever the cutoff of the theory is. So here are some of these. So this is the correction from the top. And we also have a correction from the W, for example. And we have a correction from the Higgs for the Higgs self-couplings. And all of these contribute. And this one is the main contribution. But in any case, we get something that's cutoff dependent, and it depends quadratically on the cutoff. Now, what is this cutoff? Of course, we don't know. But there's this non-trivial thing that I mentioned before, which is that if I start evolving the standard model, if I try to extrapolate it to high energies, the couplings remain perturbative. And so in principle, I can do that all the way up to the Planck scale. I don't know if that's really the cutoff of the theory, because we also saw that we need something to explain neutrino masses, which needs to be at least at about 14 GeV. But in any case, we'll get a very big contribution here. And so we'll need to fine tune this value and this value to, we'll need to fine tune them extremely precisely to many, many orders of magnitude if this is really the cutoff of the theory. So this is the naturalness problem. And we have no idea what solves it. And what this suggests is that this cutoff may be what we would want it to be, is somewhere that's around 100 GeV or a TeV, and not an extremely high scale, which would mean that there's something new going on at around the TeV, and then we can only extrapolate this. We can only, the cutoff of this theory is around the TeV, and then there's something else that's canceling these divergences. So these are the, this is the theoretical, these are the three theoretical problems, or this is the theory status of electroweak symmetry breaking. And you see that it's not, it's far from satisfactory. And the main thing that I want you to take away from here is that even before we start talking about the naturalness problem, this is really something that we put in by hand, and it's just a parameterization, okay? No more than that at this point. So you can ask, okay, what would be an alternative, or what do I mean when I say that this is not a very pleasing theoretical situation? So let me give you an example of something that does work and explain all of these things. And this is just one example, but just so you have some example in mind. So one thing that can generate the Higgs potential and provide an explanation of electroweak symmetry breaking is supersymmetry. Or what I really mean is some supersymmetric extension of the standard model. And why is that the case? So of course we know that if there is supersymmetry in nature, it's broken. And then the interesting thing is how supersymmetry is broken. But if it's broken, then there is the standard model field, and then there are all the superpartners. And all of these guys need to get some mass that splits them from the standard model particles. So let me denote all these masses by m tilde. Let's imagine that they're all sort of comparable. It doesn't matter very much. But the point is that if you start from if you have these non-zero M tildes, if you have all these SUSY breaking masses, then when you look at the running of these masses to the low scales, you find that mu squared, or let me say, you find that minus mu squared is negative. In other words, the Higgs mass parameter is driven to negative values, and we have electroweak symmetry breaking. So this is a scenario in which very, very generically, we get electroweak symmetry breaking dynamically, okay? We understand the theory, and the running drives the Higgs wave away from the origin. What is the value of this mu parameter then? Roughly, it's given by the supersymmetry breaking scale. So we understand the origin of the scale. The origin of the scale is the supersymmetry breaking scale. And then there is another thing which is important, which is that, as I said before, it's very easy to get scales, or it's very natural to think about scales that are generated from dimensional transmutation or from the RGE. So what happens in the case of supersymmetry is the following. We know that, so of course we're interested in supersymmetry breaking, but we want to imagine that supersymmetry is broken spontaneously. If we just break it explicitly, there's not much value in this. And then we know that if supersymmetry is unbroken at tree level, then it remains unbroken to all orders in perturbation theory. That's just a fact. So in that case, the only way that we can have supersymmetry breaking is from some non-perturbative effect. And so the SUSY breaking scale is proportional again to some e to the 8 pi squared over g squared. Namely, it can very easily be about the value that we want it to be. It can be many orders of magnitude below the Planck scale, but it's a reasonable number of orders of magnitude. It's like 10 to the minus 16, 10 to the minus 14. It's not 10 to the minus 80 in very reasonable theories. Okay, so very, very generically in this class of theories, we have an understanding, we have a dynamical understanding of where the scale is coming from and how electroweak symmetry is broken. So that's just one example that you can think about. Okay, very good. Another sort of example is to imagine that there's some new compositeness scale, and the Higgs is composite. That is the physical Higgs. The physical Higgs is composite, and it's coming from some new QCD. And that's how the scale is generated. So anyway, there are different scenarios, but at this point, we don't have any theory understanding of why this Higgs potential is the thing that I wrote down here. Okay, so very often you hear people talking and saying, the LHC hasn't discovered supersymmetry, so maybe supersymmetry is dead, maybe the idea of compositeness is dead, maybe naturalness is dead, that is, we have to give up on naturalness. And you can ask the question, is this true? Are they dead or not? So these are not very scientific questions, right? I mean, we're scientists, so what do? We measure stuff that we can measure, and then we answer questions to the degree that we can answer them. So the thing that we know at this point is that the LHC hasn't discovered supersymmetry, for example. So we are stuck with the naturalness problem. We do have a fine-tuning associated with the Higgs mass because we have explored, we looked for new particles on top of the standard model ones, and we haven't found them to some 1 or a few TeV, depending on the particle. So we know that we have a problem with naturalness. There's something like maybe 10 to the -3 fine-tuning. But that's all we know, okay? So what we know is that we haven't found anything new at the LHC so far. Is it enough to give up on naturalness? I would say no. There is a big question. There is a big difference between a tuning of 10 to the -3 and a tuning of 10 to the -32. And even when the LHC program concludes and we don't find anything, we still don't know, because 10 to the -3 is a small parameter, but it's not terribly small. So the answer is we just don't know. We have to keep looking, and maybe there are some super partners just above the reach of the LHC, and maybe no, but that's it. That's what you do when you, that's what you get when you do physics. Yeah. So it's a model-dependent question. Yeah, it's definitely. Many supersymmetric extensions of the standard model are ruled out. And the same holds for compositeness models. I would say that if you look at LHC results so far, things look very weakly coupled. So if anything, it looks more like supersymmetry than compositeness, unless you have really, unless you have these models where the Higgs is the Goldstone boson of some new sector, and there is a big hierarchy between them. And that's really all I can say. Yeah. Okay, so this is the motivation for me here. And the main thing I'm going to talk about is I'm going to, this is the main question that I'll have in mind. And then I want to use the EFT framework to parameterize first of all the effect of new particles or interactions at LHC energies. And the second thing is theories of electroweak symmetry breaking in a way that's completely bottom up. So that's roughly the motivation. Okay, very good. So now I want to keep thinking about this part that we discussed here, the separation of the Higgs into the Goldstone boson part and then the physical Higgs. So if we think about, so let's do the separation in a way that, let's formulate it a little better. So to separate the Goldstone bosons from the physical Higgs, what we can do, of course, is go to unitary gauge. That's what we usually do. So we take the Higgs field and we do a gauge transformation u of x, h of x of the following form. We write it as the exponential of I pi a x t a over v times 0 v plus h of x. And that separates the Goldstones from the VEV and the physical Higgs. And of course, the W, when we do this gauge transformation, the W also changes into u of x W u of x to the minus 1 minus I over G d mu u to the minus 1. And so you can say that, and so now what's happened is that the gauge bosons are no longer in the Higgs. Instead, they're residing in the W. So the longitudinal modes of the W, the gauge bosons, are now in the W. And you can say that this part of the theory, if we go back to this question of what's measured and what's not, so I can plot here the energy in GeV or the time. And the W part with the gauge bosons, you can say was measured from this observation of beta decay back in 1890s to roughly the 1990s plus, let's say. So this part here, or the massive W, that's been measured very well over many, many years. And we're now also measuring it at the LHC. So this is now at the LHC. And we're continuing to measure that up to higher energies, which are around the TeV. So this part of the theory is measured in many ways. And now let's go back in time a little bit and think about pre-LHC stuff. Let's say we're still in the 90s. So in the 90s, a lot of these W interactions were measured very well. So this is now pre-LHC. So pre-LHC, at energies that are about 100 GeV or so, maybe a little bit below that. The W was discovered, the Z was discovered, their interactions with fermions were measured, and we knew that SU2 cross U1 is broken by the W mass and the Z mass. That was the picture. And so at that point, we knew the Lagrangian of the electroweak part of the theory. It's of the form W plus mu nu, W minus mu nu, minus the same thing for the Z, minus the photon. And then we also have minus mw squared, W mu plus, W mu minus, minus mz squared, z mu. And of course, these two mass terms break the SU2 cross U1 symmetry. And that Lagrangian was measured very well. But now you can say, we're before the Higgs discovery. We don't know that there is a Higgs yet. We look at this Lagrangian, and we say, okay, we don't have a gauge symmetry because the mass terms break this gauge symmetry, but let's sort of restore the gauge symmetry. What do I mean by that? I mean that I can sort of retrace my steps and undo the unitary gauge transformation that I did before, that we usually do. And so I can just redefine the field. I can introduce a u of x, which is the same u of x that I wrote before, the exponent I pi a x t a v. And now these guys are not symmetry transformations, but some new fields. And then I'm redefining my w, just like I did before, to u of x, w mu u to the minus 1 minus I over g d mu u to the minus 1. And so now what I did is the opposite of what I did before. I took out the longitudinal modes out of the W, and I put them in this U. So I introduced new fields that soak up the longitudinal modes from the W. And the Lagrangian becomes the following thing. First of all, I have the kinetic terms that remain as before. And then the mass terms give rise to new terms, which are roughly, let me not put numbers here, but it's basically v squared trace d mu u dagger d mu u. Sorry, big D. So this is a fake gauge symmetry that we introduced, which is something that's very often useful in QFT. We didn't have a gauge symmetry, but we introduced it by introducing these, by promoting the broken symmetry parameters into fields. And now we have this fake gauge symmetry, and I can do another gauge transformation at this point, another U, under which the pi's, the Goldstones, are going to transform non-linearly. And we have something that looks like a gauge symmetry. So this Lagrangian certainly looks invariant. Everything looks fine about it. It looks like we restore the gauge symmetry. And this is something that we're allowed to do because all we did here is to redefine the fields, right? I'm just redefining the W by this, which is just a field redefinition. If it doesn't change the physics, then everything is fine. And there are many phenomena that it describes completely well. But then we're going to hit a problem, and it's very, very easy to see what the problem is. The problem is that we, in the new Lagrangian, we generated lots of interactions of these new fields, the pi's, and some of them involve very high powers of the pion fields. So for example, I can have something like 1 over v to some power times d mu pi a, d mu pi a to some power n times pi b to some power m. And we have lots and lots of these terms around. So what are we getting? We're getting an EFT, right? We now have an effective theory Lagrangian with higher dimension operators. and these are suppressed by the scale V. And what does that tell us? It tells us that if we now calculate some scattering amplitude, so now let's calculate some scattering amplitude that involves these fields. What we're going to see is that this A goes like some high power of the energy. Let's say I'm calculating some 4-point amplitude, which is dimensionless. Because remember that an endpoint amplitude in 4D has dimension 4 minus n. So this 4-point amplitude is going to go like e to the n over v to the n to some potentially very high power. And that's a problem, right? That's a problem because of unitarity. Because unitarity tells us that the amplitude cannot grow arbitrarily high, arbitrarily fast with the energy. Its energy growth can be something like e to the 0 times log e, but not any faster than that. And this is something that's completely consistent with what we know from gauge theory, because the gauge coupling is dimensionless. And so this sort of behavior tells you that this theory is not consistent. When we get to scales of order v, we have a problem with unitarity. So what that tells you is that v is the cutoff of this theory. Okay? In other words, this theory that we have here is only good at E, which is much smaller than V. And in other words, it's an EFT at best with cutoff V. So as long as we're doing experiments at energies that are much lower than the Higgs Rev, everything's fine with this theory. There's no problem. But when we get to energies that are of the order of V, we will start to see, if this is the end of the story, we'll see scattering processes that are growing too fast with the energy. So that's, here I show this using this, doing the reversing the steps of going to unitary gauge, but this is a very well-known result that you can do using standard calculations. So in particular, there is it's a problem in or a section in Peskin and Schroeder. You can look at W left at WW scattering for longitudinal Ws. I think they also do E plus E minus to WW. You can do it in using standard methods, and you find that without the Higgs, without including h of x, you have problems with unitarity. So before the LHC turned on, we didn't know what would happen, right? There was, in principle, the possibility that there would be no Higgs, and we would start to see WW scattering that violates the unitarity bound. But the Higgs is the thing that restores unitarity. So this is something that we refer to as the breakdown of perturbative unitarity. And the reason why it's called perturbative unitarity is that this is something that we see at the level of perturbation theory. We calculate something using perturbation theory, assuming that the coupling is small. And in the framework of perturbative unitarity, you see this problem unless you include the Higgs. Okay, so just a quick poll. How many of you did this calculation of perturbative unitarity and WW scattering? Okay, good. And how many of you didn't do the problem, but you know about this? But you learned about this? Okay, good. So then I'm not boring you completely. Okay, good. So I'm glad I'm saying this because, you know, there's like, sometimes you talk to people and it's like, yes, of course, you know, the Higgs is there. We always knew it was there. But that's not the way physics works. Unless you see something, you don't know whether the Lagrangian that you wrote down is there or not. You never see a Lagrangian in experiment. So these things are far from trivial. And these are actually very exciting times because for the first time, we see the Higgs, which is something that we never knew of a spin zero fundamental particle, which it seems to be. And there are many, many things that we still don't know and don't understand about it. Okay, so that's like, this is our third example of an EFT in the context of the standard model. It's the standard model without the Higgs. And it's without the Higgs, the standard model, as we said, is an effective theory with a cutoff V, okay? Which by now we measured above V, and we see the Higgs, and we see that it restores unitarity to the standard model. Okay, so that's actually a simple example, or one example, where we see the basic premise in the EFT story. So this is trivial, but I want to say this anyway. So when we talk about effective field theories, we write down some Lagrangian. And the Lagrangian contains higher dimension operators. So there's a bunch of operators. Let me call this one OD. And this D stands for its dimension, and it's bigger than 4. And as you've noticed, I'm always in 3+1 dimensions here. And so that tells you that this C here is dimension 4 minus D, which means that I can write it as some little c divided by lambda to the D minus 4. And you see that if we use this to calculate any amplitude, then the amplitude is going to go like, let's say, again, it's a 4-point amplitude. This 4-point amplitude is going to go like E over lambda to the D minus 4. And so that tells us that unitarity or perturbative unitarity breaks down at lambda. So lambda is the cutoff of this EFT. Okay, so the reason that when we write an EFT, we say that this scale is You mean a different?
Yeah.
Okay.
Here
Yeah.
we give the physical interpretation of the data, so we take the physical value.
Well,
If I'm doing this silver definition,
right, but remember, I still need to. So I just have 3 degrees of freedom that need to be here, right? Because I have the kinetic part. I want to account for the physical degrees of freedom that I have in theory. So whatever you have, you want to parameterize in terms of these guys. Whether you can have a bigger gauge group that you can. So again, I mean, it's kind of you need 3 generators to appear here.
yeah, the numerical value of V.
The numeric of V.
Yes.
No, but V, sorry. So that's, maybe I didn't say it clearly. I didn't do anything to the Lagrangian. Remember, I had the Lagrangian. Yeah, I'm glad you asked that. So I had the Lagrangian with mw squared w mu, and then the other one for z. So the kinetic part of the Lagrangian, of course, doesn't change because this is like a gauge transformation. But this part really becomes mw squared d du squared. So it's when I said v, I really meant, so this thing is some number times v. Okay, that's what I said here. Okay, more questions? Okay. Good. Okay, so that's going to be our strategy from now on, is to use this EFT language and to say that we have good motivations, we have good theory motivations, and also experimental motivations to extend the standard model to include more interactions and more more fields. But the way we're going to do that is through an EFT. So we're going to extend standard model using an EFT framework. So our Lagrangian is going to be the standard model Lagrangian plus some EFT Lagrangian. And this EFT Lagrangian is going to have the following form. It's going to be sum over I CI 6 over lambda squared OI 6, where these guys just involve the standard model fields. And then there's going to be another one with C8. Also in terms of standard model fields, and so on and so forth. And so I'm assuming here that, yeah, why not what?
Why not even the
5, yeah, it's there. You have it. And as we already saw, you absolutely need to have that, right? Because you need neutrino masses. But actually, I'm going to concentrate just on these guys, because for the most part, I'll assume that we have B and L conservation, except for the dimension 5 operator that I need for the neutrino masses. Okay, and there's actually just a single dimension 5 operator that you can write down here. Okay. Okay, good. So now that's my motivation for talking about EFTs. This is what I want to talk about from now on. But the way I want to approach this is using amplitudes and not Lagrangians. And you already saw that it's really the amplitudes that are telling us about what the scale, the EFT scale should be. And that's not surprising, right? Because the amplitudes contain information about physical stuff, right? Physical processes. Okay, so we need to discuss some basics of amplitudes. I'll try to do that very quickly. And hopefully the rest of the stuff is going to be, or there's going to be more introductory stuff in Sebastian's lectures. But in any case, we'll just mention the stuff that we'll need here. So this is the next thing that we'll talk about is amplitude building blocks. Okay. So, and since I'm concentrating on the standard model, I'm just thinking about spins that are 0, 1/2, and 1. Okay, so we have an amplitude, which is a function of couplings, momenta, and polarizations. And we'll need to write the amplitude in terms of all of these guys. And of course, for anything that's slightly important even, or basic, there are many, many ways usually to write it. So there are different ways to express amplitudes, and these different ways are useful for seeing different properties of the amplitudes. So the things that I will use here are spinors, and we'll use the most basic spinors, 2-component spinors, and we'll use them to describe both massless amplitudes and massive amplitudes. And for those, we're going to work with these little group covariant spinors that were introduced by Alkani Hamed and Huang. Okay. So I'll start with that, and unfortunately we don't have a lot of time, so we'll have to continue tomorrow, but let's at least start. Okay, so remember that for spin 0 particles, all we need in order to specify the particle is just the momentum. And in other words, there's a single, I need to specify the energy of the particle, and there's one direction associated with it, which is the direction of the momentum. For spinning particles, for spin non-zero particles, I need the momentum and I need the direction of the spin. So in general, I need 2, 3 vectors, one for the momentum and one for the direction of the spin. When we talk about massless particles, we usually work with helicity states. So we take the direction of this n to be correlated with p. So there's only one direction that appears there. But for massive particles, we don't do that. And also for massless particles, we could do something different. In any case, what we need is we need states that are characterized by P and the spin polarization. And the spin projection on some direction n. So I need to choose two directions. One is the momentum, another one is the direction of the spin, and that's how we define the particle. And the amplitude, of course, knows about that. It carries both the momentum information and the information about the spin. So let me quickly remind you what we usually do using conventional methods, or what appears in most QFT textbooks. So here's an amplitude with some number of external legs. And if we're talking about spin 1/2 particles, let's say this leg is spin 1/2. Then it comes with, let's say, a spinor USP for an incoming fermion, and U bar SP for an outgoing fermion. And I'm not gonna write all of that. And then if I have a spin 1 particle, then I need to specify. So this is, yeah, okay. So this is P, and this is P2, and this is coming with epsilon mu I of P, where I runs over 1 and 2 for m equals 0 particles, corresponding to spin up or spin down. And for a massive particle, we have 1, 2, and 3, which corresponds to, sorry, I meant to say positive or negative helicity. And here we have positive or negative helicity, or 0. Okay, and so, yeah, I think I have 2 more minutes. So let's continue. And for these vector polarizations, the things that we want is we want P dot epsilon of P to be 0. We usually choose their normalization such that epsilon dot epsilon star is -1. My metric, by the way, is mostly minus. And so, for example, if I have a massless particle, a massless spin 1 particle with P, that's P 0, 0, P, namely along the Z direction, then epsilon mu of P and plus minus or 1 equals 1 over square root of 2, 0, 1, sorry, minus or plus 1, minus I 0. And if we have a non-zero M and our P is E 0, 0, P, then we also have a third one, which is P over M 0, 0, E over M. Okay. And with this, we can write down the amplitude completely. But the thing that we want to do here is to write both the momenta and polarizations in terms of the basic building blocks of Lorentz. So we're going to write both the momenta and polarizations in terms of spinors. And that's because we know that the Lorentz group, I can think of, I can split that into an SU2 left times an SU2 right. So I can write any object that transforms under Lorentz in terms of the basic building blocks of these two SU2s. So these are spinors, which are 1/2, 0, or 0, 1/2. And then any higher representation we can get by combinations of these spinors. And in principle, and in general, when we take combinations of them, the only thing that matters is symmetric combinations, because the anti-symmetric combination just gives us the singlet. So two spinors that are combined anti-symmetrically just give us the singlet. Okay, so I'm going to denote these guys by lambda alpha, or an angle spinor, and these guys by lambda tilde alpha dot, or square spinors. And these are redundant notations. I mean, I don't need both this and this, but sometimes they'll show up, so we'll write them anyway. We can raise and lower indices here with the Levi-Civita tensor, epsilon alpha beta, or epsilon alpha dot beta dot. And we're gonna take, our convention is gonna be that epsilon ij equals minus epsilon ij, and epsilon 1, 2 equals 1 for any set of each one of these sets of indices. And we can contract spinors in this way. Lambda chi, for example, is going to be epsilon alpha beta, lambda alpha chi beta. And this is equal to lambda alpha chi alpha, and this is equal to minus chi lambda. And similarly, lambda tilde chi tilde is minus chi tilde lambda tilde, and is equal to epsilon alpha dot beta dot lambda tilde alpha dot chi tilde beta dot. Okay, so I guess I'll stop here and we'll go on with this tomorrow. But any questions before we break? Okay, let me ask you though, how many people here did not see spinor formalism? So everyone knows meshless spinors. What about massive spinors? So, okay, who knows the little group covariant massive spinor stuff? Okay, so maybe we'll spend a little more time on that tomorrow. Okay, good.